Okay, well, welcome everyone to the second day of this workshop. So today's topic is basically quantum advantage. So we heard yesterday about how our quantum computers are getting better and better, and we have to figure out what to do with them. So that's what we'll talk about today. So our first speaker is Andrew Gheorghiu from IBM, who's going to tell us about some old and new ideas for verifiable quantum advantage.
Thanks, Anand.
Oh, wait, and one announcement. So just if there are questions, I guess during the talk, Andrew, if you could just repeat the question for the recording, and then afterwards, in the question session afterwards, I'll pass a mic around.
You might have to remind me because sometimes I forget. But yeah, I'll do that. Yeah, so thanks a lot, and thanks for having me here to give this talk. So I should say that the original intention with this talk was to give like more of an overview for the existing approaches to verifiable quantum advantage, and then at the very end to talk about this new approach that we have at IBM. But I realized that I wouldn't have enough time to properly do that approach justice. So therefore, I've significantly shrunk the overview part, and I'm mainly going to focus on this new idea. So to get us started, let's actually define what we mean by verifiable quantum advantage. So we want some computational task that is efficiently solvable on a quantum computer, i.e. in polynomial time, and which should be hard to solve classically. Hard meaning, not in polynomial time. Ideally, it should take exponential time to have like the maximum possible separation. We also want this task to be efficiently verifiable classically. So when I get the results from this task, I should be able with a classical computer to check that they're the correct results. And ideally, we also want that this is something that we can implement in the near term. So either on a noisy intermediate scale or NISQ device, or even on an early fault-tolerant device where the amount of noise can be very small, but the number of qubits that you have, like logical qubits, is also very small. And we might also care that it's a useful task, but as a theorist, I think I'll declare victory if we can achieve the first three conditions. Okay, so here is the briefest history of approaches for verifiable quantum advantage. So we had these first classic algorithms in the beginning, like Simon's algorithm, Shor's algorithm for factoring and discrete log, and quantum simulation. These are maybe like the most convincing algorithms that we have for demonstrating quantum advantage. The problem is that they typically require a very large implementation overhead. So we don't think that there are things that we can do in the near term. Although I will say a few more things on the factoring side a bit later, because there have been some recent interesting developments. Then as these early quantum computers were being developed, people started thinking like, okay, can we come up with quantum advantage tasks that we can run with like a small number of noisy qubits? And this led to like these sampling-based approaches, like boson sampling by Aronson and Arkhipov, IQP, or these like commuting circuits, and then like random quantum circuits. So these are approaches that like really fit within a small qubit budget. The problem is that they're typically not efficiently verifiable. And they can also be spoofable if your circuit is noisy. At the same time, people were developing like more heuristic approaches to quantum advantage inspired from machine learning. So you had these variational methods, QAOA, variational eigensolvers, and so on, which again, they're meant to be practical. They're meant to run on a small number of qubits and on noisy devices. And here you would have verifiability as well. But now it's a bit unclear if the task that you're solving is actually classically hard or not. More recently, there have been these so-called interactive proofs of quantumness or tests of quantumness, where now instead of like delegating a problem to a quantum computer and getting back an answer and just directly checking that answer, you can have an interactive protocol with the quantum computer where you can send the quantum computer a challenge, it responds, based on that you send another challenge, and so on. And what's nice about these protocols is that you can typically base classical hardness on very well-established cryptographic assumptions. And these assumptions need not even be like quantumly, they need not be only classically hard. So you can also construct protocols that give you quantum advantage even based on problems like learning with errors, which we believe is a quantumly intractable problem. And this is really because of the magic that we get by making things interactive. But again, the downside with this, similar to like the early algorithms, is that they tend to require fairly large overhead, so they're currently not practical to run on the devices that we have right now. And now, like even more recently, there have been these, I call them like code-based approaches. So one was this Yamakawa-Zandri algorithm, which kind of relies on duality properties of certain error-correcting codes. And more recently, there's been another version of this called decoded quantum interferometry from the Google group, which seems like it might be able to solve certain optimization problems. And again, here, like similar to the interactive protocols and like old quantum algorithms, these seem to have a very high implementation overhead. There's maybe some hope that DQI could give you something that is more practical in the near term, but then there might also be a question with DQI about the classical hardness of the task that you're solving. So, I stole this slide from one of Scott's talks with this, Venn diagram of the state of affairs. And I guess I also stole the first part of the title of his talk. Hope that's okay, Scott.
I'm honored.
So, you can kind of see in this plot basically a summary of what I just said. So you have these three circles of like Niskable, so implementable in the near term, efficiently verifiable, and in principle quantum advantage. And we can see that all of the approaches we've developed so far tend to fall in only two of the three categories. And we don't yet know if there's something that's like really in the middle. At least we don't have something that's like truly convincing that is in the middle. Okay, so before telling you about an idea that we had, which we think might lie in the middle of that Venn diagram, I just wanted to like bring up some really interesting recent developments in quantum factoring, where it's been shown that you can significantly reduce the resources that are required to factor. So there was this paper by Craig Gidney showing that you could factor 2048-bit RSA integers with less than 1 million noisy qubits. And this makes use of some very clever space optimization techniques that I guess we're going to hear about in the next talk. And at the same time, there was also this other protocol that was developed for factoring numbers of the form p squared times q. And it was shown in this paper that the factoring circuit for these types of numbers can be like even smaller than the circuits that you would have for like normal, like semi-prime factoring, so numbers of the form p times q. So I kind of took this table from their paper to kind of show you what the asymptotic scalings are. So the first 3 rows here are, like let's say standard factoring algorithms for numbers of the form p times q, but like with different types of approaches. And then these last two, so the second to last one is to determine, I guess, the square-free decomposition of an integer, and the last one is this Jacobi factoring circuit. And you can kind of see that this last one seems to have the most favorable parameters, at least in terms of numbers of qubits and the depth of the circuit. So it's even like sublinear, which is really nice. So this is all to say that it could be that even these factoring-based approaches could give us like very early demonstrations of verifiable quantum advantage on like early fault-tolerant devices. So maybe like devices that have under 1,000 logical qubits, something like that. And I think if you talk to Greg, like the first author of this paper, he might convince you that Jacobi factoring might even be doable on a noisy device as well. But I guess this remains to be seen. And one last thing I want to mention here is that with factoring, the classical hardness that we have is not really like, say, exponential in n, but it's usually exponential in like the cube root of n, so like slightly sub-exponential, which means that you'd have to take n to be like fairly large to get a number that is at least currently classically hard to factor. So maybe around like 800 bits is, I think, the largest number that has currently been factored. And this will directly impact the resources for your quantum algorithm. But on the other hand, if one were to look instead at computing the discrete log instead of factoring on elliptic curve groups, the advantage there is that the classical algorithms for like breaking elliptic curve cryptography really scale as like almost exponential in n. So the key sizes there, instead of being like 800 or 1,000 bits long, they're usually like hundreds of bits long, like 200 bits, 400 bits, and so on. So the point of this is that if one could come up with similar types of savings and like clever approaches to do the discrete log quantum algorithm on elliptic curves, then we might see an implementation that breaks elliptic curves in like 300 logical qubits or 400 logical qubits, so something even smaller than factoring. Okay, so before moving on, maybe just to pause a bit if there are any questions about the state of the art, although like on this stuff, probably the questions are better suited for the next speaker. Yeah.
Has anyone done a detailed analysis for the elliptic curve thing?
Yeah, so I know that there are a number of papers, but to my knowledge, the analysis has not been as detailed as like Gidney's analysis for factoring. But I think the state of the art is that you need maybe like 900 logical qubits to break elliptic curves that give you 128 bits of classical security. So it's under 1,000 qubits, which is nice, but the question is, can we push it even lower?
Right.
Any other questions? Okay, oh yeah.
I guess, but there's also the question, right, of I think in that like 900 qubit circuit, like the gate count is rather, right? Like the block clock runtime would probably be quite long, or I don't know if you know.
Yeah, I don't remember. I thought it would be comparable to factoring at that size. Maybe I'm wrong. Yeah. Okay, so now let me spend the rest of this talk talking about a new approach that is based on joint work with Sergei Bravi and Kristan Teme. So this is not out yet, but we hope to have the paper out fairly soon. And I should really say that this was really their idea, and my contribution to this is fairly tiny. I've mainly been thinking about like the classical hardness. So like all of these ideas, if you think they're really nice, then you should credit them for it. So this approach is based on a very interesting problem from 2009 called Forrelation, which Scott introduced. So this problem is as follows. Suppose you're given access to two Boolean functions, f and g. And what you basically want to determine is how correlated is f to the Fourier transform of g. So this boils down to computing this quantity. So this seemingly ugly-looking sum over here. But as we'll see, there's like a very simple quantum circuit whose like amplitude of outputting 0 will be exactly this quantity. So given access to these two functions, you want to determine if this quantity in absolute value is fairly large or fairly small. The constants here are fairly arbitrary. I believe they were chosen this way to make the quantum algorithm only have to do one query to f and one query to g. So the algorithm just looks like this. So first you create an equal superposition over everything. Then you evaluate the unitary implementation of f. And by that I mean a unitary that evaluates f in the phase. Then you just Hadamard again. You do the same thing for g. You Hadamard and you measure. And the zero outcome, so the all zero outcome of the measurement, its probability will be the square of this quantity. So that's what you will look at and see whether it's small or large. Okay, so yeah.
So the idea here is you only have to answer the question when it's one of these two.
Yes.
And then determine if it's one of those two, which it is.
Yes. Promise that it's one of the two. Yeah, that's right. Any other questions about the? Yeah.
So I consider this quantity?
Sorry?
Why consider this quantity? Does it show up in other places, or is it just a problem?
Oh yeah, it's just a problem. So it's because it's because it's exactly the output amplitude of this circuit.
Because it's hard classically.
Yeah.
Does that answer the question?
Absolutely.
Yeah. So we're not trying to solve the usefulness part yet. Okay. So before telling you like how we can use Forrelation to construct a verifiable quantum advantage test, let's make some observations about it first. So this is the quantity that you want your quantum computer to essentially estimate. And what's interesting is that Forrelation satisfies a very interesting symmetry property. So suppose that A here is a binary orthogonal matrix. So it's a matrix with binary entries such that its inverse is basically the transpose. And this is the binary orthogonal group on n-bit vectors. So I should say that from now on, all the operations we'll be considering are mod 2 operations. So everything is over F2. So it turns out that, kind of similar to when we learn about unitaries, that they preserve the inner product, these binary orthogonal matrices will preserve the binary inner product between bit vectors x and y. So you can kind of see here that if I start out with like a times x, a times y as binary vectors, and I want to compute their inner product, their dot product, you can just rewrite it in this way, and it ends up being exactly the dot product between x and y. So what this means is, suppose we consider these alternate functions f prime and g prime, which are just f evaluated on a times x, and it's basically like a change of variable. So it's like if you're a physicist, it's like a gauge symmetry, I guess. Oops. What happened? Yeah. So then the expression for correlation between these new functions f prime and g prime will look like this. So it's the same as before, except you have a times x and a times y here. But now if we make a change of variables, so let's say we denote u as a times x and v as a times y, then I can just rewrite this as -1 to the f of u, -1 to the g of v. And then here, what was before -1 to the x dot y now becomes a inverse times u, which is x, dot a inverse times v, which is y. And because these matrices preserve the inner product, then this is the same as u times v. And so this quantity is exactly the same as the original. So correlation is essentially invariant under these like affine orthogonal group transformations. Okay, so the two correlation quantities are the same. Okay, so that's one observation. Here's another observation. So suppose that we consider, instead of just regular correlation, we consider something that we'll call self-forrelation, where you just take the g function to be the f function. So you basically just want to know like how correlated is f with its own Fourier transform. So the circuit for computing this would now look like this. And now this will end up having a very nice form because you can just express it as like these Hadamards acting on all zero just give us a bunch of plus states. And we're trying to measure the all zero outcome. So we're projecting on all plus. So you have pluses on this side and then this phase oracle for f, then this Hadamard in the middle, and then phase oracle for f again. And now if I simply denote as ket f the state that I get by applying the phase oracle on the plus states, which simply means it's an equal superposition where in the phases I have the evaluation of f, right? Then what I'm asking for is essentially the expectation of the Hadamard observable. Like the correlator just becomes the expectation of this Hadamard observable. So this means that you can slightly simplify the circuit. You can just prepare this state, this f state, by just doing like Hadamards in UF, and then making a measurement in with respect to the basis of Hadamard to kind of estimate the expectation value of this observable. And so, with these two observations, our goal now is, can we construct a version of correlation that's classically hard to solve, but is easy to verify and still retains the fact that you can compute it quantumly? And the first question, yeah.
Sorry, just like,
yeah.
The dagger missing?
Where? I mean, everything is kind of self-adjoint here.
Okay.
So, yeah.
Okay.
Any other questions? Okay. So, to turn this into a test of quantumness, the first question you might ask is how do we actually instantiate these f and g functions, or say just the f function if we're considering this self-forrelation? So, for computer scientists, a very natural choice is to consider low-degree polynomials. So suppose f is, say, a degree 3 polynomial over f2. So I want to really emphasize here that the polynomial is over f2, so it's over bits, it's not over the Boolean hypercube. This will be very important later on, but maybe you can ask me about it later if this point is unclear. But it's literally just a function of this form that I've written here, where these x, so you're looping over all products of like groups of 3 bits of the input x, and each one will have a coefficient which is either 0 or 1, and the addition here is just mod 2 addition. Okay, and this is just product, which is the same as like logical AND between these things. So this is a degree 3 polynomial over f2. This is all well and nice, but this, it's not clear like how would I actually compute the correlator for a degree 3 polynomial. So what I want to do to kind of make the correlation task easy initially, and then I'll try to make it hard again classically, is to actually say, not only is f a degree 3 polynomial, but it's actually a sum of very small polynomials, also of degree 3, that just act on like groups of k bits. And these k bits are all disjoint from each other. So what I mean is, it's a sum of n over k functions f1 up to f sub n over k, where each one of these acts on k bits, and the first one acts on the first k bits of x, the next one acts on the next k bits, and so on, right? So it's just this very simple construction here, and k you should think of as either a constant or at most logarithmic in the size of n. So it's not too difficult to see that if you do this, then this phase state that we saw before, so this state where it's an equal superposition over everything and you have the evaluation of f in the phase, it's just going to become a product state where you have like all of these like smaller functions in there. And so the correlation itself then just becomes the product of like the self-forrelation of each individual fi function. And now because k is fairly small, like it's a constant or it's logarithmic in n, then you can just classically compute all of these quantities and then take their product, and that gives you the self-forrelator for f. So now everything is efficiently computable classically. So that's great, but now how do we make it classically hard again while still, say, retaining knowledge of the correlation? And this is where we'll use this property of the symmetry under affine transformations. So what we're going to do is instead of yeah.
I have a different worry here, which is
sure.
Won't this just generically become exponentially small, right? Unless we do something careful to prevent.
Yes, that's true. So you have to choose these FIs so that the individual self-correlations are fairly large.
Yes.
And you can do this. So there are these functions called self-adjoint bent functions, which achieve this property and which can be implemented as degree 3 polynomials. Yeah. So it is, I'm sorry, I forgot to repeat Scott's question. So the question is like, won't this quantity become exponentially small because we're taking a product of like n over k things, and if each one of these was, say, a constant bounded away from 1, then this would just decay to 0. But it turns out that there exist choices for this, for these polynomials f that would make each one of these f's, each one of these phi's, sorry, to be like, say, either +1 or -1. Mm-hmm. Yeah.
Do you know that for a fact? Like if you choose these alphas to be random, that it's exponentially small?
Well, you can prove it, yeah. So I know, yeah, it's definitely true.
Can you repeat the question?
Oh, sorry. The question was like, if you choose the alpha coefficients to be random, will the correlator actually be small? So I think this is true. Yeah, like I think it shouldn't be too difficult to prove actually.
Bounded away from 1. That's basically what.
It's bounded away from 1, but I think it actually converges to 0 on average. if the coefficients are random. Yeah.
Where are you using the low degreeness of f here?
So, right, it's not explicit yet, but we'll use it in the fact that you need to somehow specify these functions, and polynomials you can just specify as a list of coefficients. So if it's a low degree polynomial, then you just have a polynomial number of coefficients that you have to specify. So these alpha coefficients. Any other questions? I haven't actually told you what we're going to do yet, but you can probably guess. Okay, so here's what we're going to do. So with probability a half, we're going to decide, do we want to construct an instance of forrelation where the magnitude is large or small? We're then going to choose these fi functions appropriately. So if we want to make it large, then we can choose each one of them to be very close to 1 so that the product is close to 1. If we want to make it small, we can choose random values, and then it's going to be close to 0. Then we're going to pick a random matrix A, and then we're going to compute the coefficients of like f prime of x, which is f of ax. So as I said, because this is a low degree polynomial and it's degree 3, the number of coefficients is like on the order of n cubed. So you can just compute all of them in n cubed time. We're then going to send these coefficients to the quantum computer, and then we're going to ask it, just perform self-forrelation with this function and tell me if the value is large or small. And the hope is that this orthogonal affine transformation is effectively hiding, this product structure of f that we've constructed, so that if you're just given the, say, obfuscated or like scrambled thing, you don't actually know whether it was like a small or a large value for forrelation. Like you don't know what the individual fi's will be. And so in terms of implementation, this is only going to require, only quote unquote n cubed gates and n squared depth. So it's n cubed because, again, it's like a degree 3 polynomial. So you effectively have to, when you're doing this like UF unitary, you have to implement each term in the polynomial, and there's like order n cubed of them. And as far as we know, the best classical algorithms for forrelation take roughly exponential time, like 2 to the n over 2. So at least superficially looking at this, it seems that like taking n to be even as small as like 200 would be good enough to give you quantum advantage.
And the degree 2 case is easy classically?
Good question. So the degree 2 case is easy because then the circuit is Clifford. And then you can just simulate it classically. Yeah. So degree 3 is like the smallest one where you have a non-Clifford circuit. Except this turns out to not be classically hard. So here's what happens. So this is the genius of Sergei Bravi. So he realized that there's actually a classical algorithm that can estimate the square of the forrelation to within like a small additive error in polynomial time, specifically for degree 3 polynomials. So interestingly, it doesn't work for higher degrees. So as I'll say later, you could consider degree 4 or higher. But let me just kind of give like a very sketch of how this argument works. So the square of the forrelation you can just express as this quantity. So this, as we said, is the Fourier. It's like the expectation of this Hadamard observable on f. And we're just taking the product of 2 of these. Notice that I don't have to worry about complex conjugation because everything is real. And then I can just view this as like having 2 copies of this f state and looking at the expectation of this observable. So now let's consider this state, which I'll denote as psi f, which is Hadamard applied to only 1/2 of 2 copies of f. And it's not too difficult to see that this thing from above can be expressed as like psi f and then a swap that swaps like the first n qubits of the state with like the second group of n qubits of the state, and then another copy of psi f. So this swap is, so if you look at like psi f, it has this form, and you have it on both sides, but the Hadamard is like on the first n qubits on both, and the swap is basically moving the Hadamard on the bottom one. So then you get the thing from above. So you can show with like some clever algebra that I won't really get into, that you can then express this phi squared as effectively the empirical mean of a random variable. So this PF of y is a probability, so it's just like a basis vector on 2n bits in inner product with this psi f state squared. And this RF is this fairly ugly looking expression. So you can get this by just introducing an identity here and then expressing it as like a sum over all computational basis states. That's where this comes from. So this is the empirical mean of this random variable RF, which you can show has variance 1. And it turns out that this random variable can be efficiently computed classically, and this probability distribution can be efficiently sampled from classically, specifically in the case where f is a degree 3 polynomial. And the proof of this is quite technical, but I'll give you just like a one-line high-level intuition for why this is the case. The reason this happens is because when you take these two copies of f this way, and you look at like the inner product between a computational basis state and this state, like Hadamard and then two copies of f, you can show that this ends up being a sum of -1 to some function h, and this h turns out to be the derivative of f. So if f is a degree 3 polynomial, then this h is a degree 2 polynomial. And we know that for degree 2 polynomials, you can actually compute the number of solutions that they have classically in polynomial time. This is also sometimes used for these like classical simulators of Clifford circuits, because with Clifford circuits, you usually get quadratic forms. So the insight here is that by using these like two copies, by computing the squared of the correlation, you can make it so that all the sums that you would get in these quantities only involve degree 2 polynomials, and then you can just efficiently compute them classically. And you can also compute like any marginal of this, and then this allows you to efficiently sample from this probability distribution. So then once you can do this, you just do a Monte Carlo estimate of this. So you just sample some y's according to this probability distribution, compute the corresponding R quantity, and then just sum those up. And you can show that this will converge to f squared, and you'll have just an additive error of, if you want to estimate it to within error epsilon, then you just need like 1 over epsilon squared terms to compute it. Yeah.
Wait, just to be clear, so here you're using the degree 3 property for both the sampling from PF and to compute RF.
That's correct. Yeah, because to compute RF, this still boils down to computing something like this, right? Because the swap, if I view it as acting on this state, it doesn't really do anything, right? Like on the y. So you're really still computing just inner products between like some basis vector and the state of the form psi f. Yeah.
Is there some easy way to see that it's indeed this derivative? What's the intuition behind it?
Yeah, I don't know that there's an easy way to see it. Like the proof is fairly involved. Maybe there's a simpler way to see it, but like the only thing I can really say is that it really comes from the fact that you're taking two copies of f. And is there a marker? Like what you'll end up with in this h is, so this h will be something like h sub y of x will be something like f of x plus y and then plus f of x. So it's like the derivative in the direction of y with respect to, yeah.
But if you take 3 copies, can you get 2 derivatives? Like have you?
Yeah, so I actually asked Sergey this before the talk, but he didn't reply yet, so I don't know. I think you'd actually have to take like four copies instead of 3. But
Can you repeat the question?
Oh, sorry. The question was like, if you take more copies, can you get higher order derivatives?
Yeah.
So I don't know. I think it might be possible. And then that means that, for any low degree polynomial, you can compute basically the magnitude of the correlation.
Like if D is a constant.
Exactly. Yes, that's right. Okay. Any other questions about this? Yeah.
Do you have an opinion on like, what if you go to like degree 10 polynomials? Do you think that is going to be, there's going to be something classically hard, or maybe all polynomials?
Yeah, so Okay, so the question was, if we go to higher degree polynomials, will we get something classically hard? So, it seems like if all you're trying to do is estimate whether the correlator in magnitude is large or small, then if it's hard to compute these higher order derivatives, then it could be the case that taking higher degrees would be fine. But if by using multiple copies you can compute these derivatives until you reduce the computation here to something that is degree 2, then for any constant degree it would be easy to do classically. Like you could do it in polynomial time. Any other questions about this?
I have a quick question. So you said that for degree 3, there's a family of polynomials that ensures this product stays large.
Yes.
Is this true for other degrees?
Yes.
Okay.
Yeah.
Every degree above.
Yes.
Every degree, basically.
Every degree. Yeah, that's right. Yeah. Okay. Yeah.
Okay. So you mentioned that you're taking k to be roughly log n.
Yes.
So why don't just take a completely random function? Besides, this can be specified.
On k bits. I see.
Like the implementation will be from.
Yeah, so the implementation would be. Oh, sorry. the question was given that we're taking this k to be log n, why even restrict to low degree polynomials? Why not just take a random function?
Yeah, good.
So you could do that, but then so then it's not clear that the f function, you would still have a compact classical description of it when you do the affine transformation. If it's polynomials, then you simply need to send the coefficients. If it's not a polynomial, then when you compute this f of a times x, then what would you send to the prover for it to be able to implement this, to the quantum computer, I should say, without actually revealing a itself?
The degree is k at most.
Yeah, so I guess it's true, but if it's log n degree, then you would need n to the log n coefficients. Yeah. So the answer is it's not clear that you can still compactly specify the function. Okay, so here is so I wrote here that the previous approach fails when f is degree 4 or higher, but this is subject to this question of whether you can compute higher order derivatives or not. And the number of gates to implement will always scale as n to the degree of the polynomial. But here's an interesting way to fix the problem. So the previous approach also fails if you actually just want to compute the sign of the correlator instead of its magnitude. So if you want to compute, what is, so again, assume that the correlator is large, it's close to +1 or -1. But I just want to know, what is its sign? Is it +1 or is it -1? Then you can't do the thing that we did before, because the thing that we were doing before is really tailored to computing the square, because this connection between having 2 copies of f and getting this derivative of the function. And the correlator itself would only require 1 copy of f. So it's not clear that you could modify this approach to make it work to actually compute phi itself, not something like phi squared or its absolute value. Okay, so then, as you might expect, we can just modify the approach that we had before to say, with probability 1/2, decide if the value of the correlator should be, strongly positive or strongly negative, choose the appropriate functions fi to kind of achieve this, apply the affine transformation, send the coefficients to the quantum computer, and then ask the quantum computer to compute whether this is positive or negative. And again, this just boils down to estimating the expectation of this Hadamard observable. And then we just check the result. So maybe I should just pause here to ask if there are any questions about this. This is basically our candidate. So far, we've not been able to break this classically, to come up with an efficient classical way to do this. Yeah.
This might be where you're going, but can you talk about the hardness of the deobfuscation?
Yeah, so that's, sorry, so the question was, can I talk about the hardness of the deobfuscation? So that's what I'll talk about next. But if there are any other questions before that, yeah.
when you say you choose functions for which the self-correlation is large,
yes.
Are you just going to pick it to be +1 or -1, or are you also going to choose other values?
Yeah, I think you can just pick them to be +1 and -1. So if you choose other values, then it's kind of nicer because you have a larger space of functions to choose from, and that could potentially make the problem harder. But because of this issue that the correlator is just the product of these smaller correlators, you have to choose each one of them to be like 1 minus 1 over poly, essentially, so that the product of all of them doesn't decay to something negligible.
But as far as you're aware, if I just choose them all to be +1, -1, this might still be classically hard.
Yes, yeah. Like as far as we can tell, we don't know how to break it in that case. Yeah.
How many such degree 3 polynomials are there?
Yeah, that's a good question. So.
Repeat it.
Oh, sorry. So the question was, how many such degree 3 polynomials are there? So I don't know exactly. I believe asymptotically it scales exponentially. And what I do know is that if these FIs are acting on 6 bits, so you take k to be 6, then there are around 42,000 choices. There's like a thesis that we found that kind of lists. So again, if you search for like self-dual bent functions, you will find this.
And can they further be like efficiently generated? Well, I mean,
yes.
Obviously okay.
Yeah.
I mean, when it's 6, it's just a constant number. But
yeah.
In general, there is some efficient.
There is, yes, there is an efficient procedure. Yeah.
Will you have a slide about that?
No. Sorry. Any other questions? Okay. If not, then let me just talk a bit about how hard is it to try to invert this affine transformation. So unfortunately, I don't have too much to say about this because pretty much everything we've tried to show has failed. But okay, let's look at it from this perspective. So we said that our f function is the sum of these like smaller fi polynomials. And each of these FIs, if it's a degree 3 polynomial, I can just write it like this. And the coefficients here, alpha, are indexed by J1, J2, J3, so the terms in the polynomial. And the superscript I just labels whether it belongs to the FIth function or not. So if f prime of x is f of ax, and we write this again as like in terms of its coefficients and we denote them as beta, then you can show that applying the affine transformation gives you this expression for beta, where again, like everything here is mod 2 again. So you have like the alpha coefficients and you have basically like products of 3 from the entries of the A matrix. And you can see that essentially these beta coefficients of this f prime function, so the coefficients that we're sending to the quantum computer, can be viewed as degree 4 polynomials in the entries of like the original coefficients that we have, the alphas, as well as the entries of the matrix A, right? So this is basically a degree 4 polynomial. So what you could try to ask is how hard is it to invert this? Like if I give you all of these betas, and you know that it has this form, how hard is it to solve basically and find the alphas and the A's? And one thing that we've been trying to show is that this seems related to the hardness of solving systems of like multivariate polynomial equations, which in general is classically hard. But of course, we don't know if it's classically hard for this specific case, like when you have this specific form of these degree 4 polynomials. Another perspective you can try to take is to say, let's view this transformation as a pseudo-random generator. So it's taking the input coefficients alpha and this matrix A, and it's giving you this list of beta coefficients. And notice that like the number of alphas is just linear in n because you'll have like roughly k cubed coefficients for each of these FIs. And the number of these FIs is roughly order n when k is a constant. So you have like basically, I guess, well, n times k squared of these coefficients. So you have like linearly many alphas. The A is quadratic, so it's like order n squared. On the other hand, this beta is going to be on the order of n cubed because it's like the list to the coefficients of a degree 3 polynomial. So you're effectively mapping n squared bits to n cubed bits. And this is like a pseudo-random generator that is expanding with an expansion factor of like n to the 1.5. And this is very similar to what are called like low complexity pseudo-random generators that people have looked at, where they've taken like, very simple functions like usually constant depth classical circuits that can do, these like expansions, particularly for a factor of like n to the 1.5. So I think like Oded Goldreich had one of the first proposals for something like this. And since then there have been others. And as far as I know, no one has been able to prove that it's actually hard to break Goldreich's PRG, but at the same time, no one has been able to break it. Instead, you can show certain properties like that, the sum of squares hierarchy at like every linear level will fail to distinguish the output of this from a truly random number, or like certain, classes of local algorithms will fail to distinguish this from a PRG, and so on. So you can essentially show that like certain families of algorithms cannot distinguish the output from truly random. But whether this is true, in this case as well, is unclear at this moment. This is something that we're still trying to figure out. Yeah.
If it is a PRG, then would the quantum computer break the PRG?
Yeah, so the question was, if it is a PRG, then is the quantum computer breaking the PRG? So I've kind of gone back and forth on this. I'm not really sure because, the quantum computer is still not able to it's able to compute the sign of the Forrelator, but it's still not able to, like, it's not clear that you can actually invert the mapping by using this. So like actually figure out what the original polynomial was. So it might be a PRG that's like even quantumly secure in that sense. And I should say that like even if you prove that it's a PRG, then you've merely shown that this problem should be at least as hard as solving it for like fairly random polynomials. Promise that their Forrelator is like very high in absolute value, right? Like that's what you would be reducing it to if you could show this PRG property. Yeah, do you have a, yep.
Have you just tried to be, like, if you use some fast Grosvenor basis implementation on a moderate size, right, of the problem?
So, sorry, a fast what?
Grosvenor basis?
Oh.
Like Faugier's F5 or F4 in 4GB or something.
Yeah,
like
we
stat solvers, but for polynomial systems with multivariate.
Right. We haven't tried yet. We do want to do that as well. First we were just trying to see if we can base it on some existing classical crypto. But yeah, that's definitely something that we're going to do before putting out the paper to kind of give more convincing evidence. Yeah.
I guess following Robin's question, if you make it like plus or minus one value, like it's a correlator to plus or minus one value.
Yeah.
Does this problem look simpler or is it easier to work with?
Yeah. So I don't know. So you would also be, so obviously there are some constraints on the alphas here that are not, captured here, right? Like these alphas are not just random, they're constrained so that these functions are these like, self-dual bent functions that achieve this like plus one minus one thing. But, even in this case, it's not clear to us what you can do to try to recover the coefficients, even if you make this restriction. Because the number of choices will still be exponential. Yeah.
What if you fix the band function? Is it clear that would get compromised?
Sorry, I forgot to repeat the question. So the question is, if you fix the bend function, then is it compromised? So do you mean like make all of the FIs the same, like the same coefficients, or?
So yeah. So suppose that all you are doing to hide the function is picking random subsets and then the matrix A, right? The matrix A.
You mean like random subsets of k bits, or? Oh, I see. Good question. I'm not sure, actually. I guess we've mainly been thinking about it where the blocks are kind of known, like it's like the first k bits, the second group of k bits, and so on. But yeah, like if you were to take random subsets of like disjoint k bits, yeah, it seems like that could help. I guess that's in some sense like also adding a permutation.
But wait a minute, once you have the A, doesn't that already include, doesn't that like subsume permuting the coordinates?
Oh, yeah.
Because, a linear transformation could do that also.
Yeah, I think that might be correct.
Yeah, right.
Yeah.
I think the question was like if you don't choose a random alpha, but just have like some fixed alpha that's like +1 or -1.
Right, but if the alphas are fixed, then
but the A is still random. Yeah.
The A is still, but do you mean like the alphas are the same for all of the FIs?
I think that was the question.
Same and known in everything.
Sorry?
Same and known in everything except for A.
Yeah, I guess I'm not sure I fully understand the question, but it feels like if you just fix the alphas, then can't you just try them, like classically, and see like which, oh, but you still don't know what the A matrix is. Okay, I see. Yeah, it's a good question. Yeah, it might still be. I guess classically, at least intuitively, it doesn't seem like there's an immediate way to be able to check. Yeah, like to determine, like what the forrelation value was, or like the sign of the forrelation. Yeah, so that could also work. I mean, it wouldn't really give you any savings in terms of like implementation overhead or anything like this, but I guess it's a good question to think about because it might be easier to tackle to see like, can we at least solve this classically? And if we can't even solve that, then the more general case should be harder. Any other questions? Yeah.
So is kind of the idea, you know how to sample bent functions?
Yeah.
The A's will give you something that might not be bent, but it still has large magnitude correlation.
Right, so the question was, are we sampling bent functions and then the A transformation makes it so that it's no longer a bent function, but you still know what the correlator is. I think the F prime function will still be self-bent. It's just that, because like you're essentially hiding the product structure of F by applying this A transformation. So your original F, at least if you think about it in terms of like this tensor product of these ket F states, has this very nice like, tensor product of like very small states. And then when you apply this A transformation, you get something where this like product structure is now hidden, like you don't know what it is anymore.
So
yeah.
You must have thought about like, what if you use the polynomial factoring algorithm? Are there factoring algorithms that could somehow recover the hidden product structure?
Oh, I see. But it.
You should repeat that actually.
Sorry. So the question was like, what if you use the polynomial factoring algorithm? Could that recover the product structure? Yeah, that's a good question. So I think Sergey may have tried this, but I'm not exactly sure. It's not clear to me that this like F prime will still have any sort of like product structure, right? Like it's more like there's an equivalence class of polynomials that all have the same correlation value under this affine transformation. And we're starting with one which is in product form, but then we're mapping it to one which might not have this form anymore.
Oh, it's not. It's like not the same polynomial. So factoring.
Exactly. Yeah. It's definitely not the same polynomial. Yeah, it's a different polynomial.
Can I ask what is the polynomial factoring algorithm? Is this just like a canonical algorithm?
You should ask Scott.
but wait a minute. I mean, if I first do some linear transformation of the coordinates, then I get a bunch of linear combinations of the coordinates. And then I'm again taking low degree polynomials in those and taking the product of those, right?
Yes.
So it should be factorizable.
I see.
Unless I'm
It's a sum.
Unless I'm making a mistake.
It's a sum, not a product. So,
Oh.
sum over.
Yeah, like this F is a sum of these
right.
things, but
Good. Thank you.
yeah.
Got it. Yes.
Yeah, I meant that the states are in product form, like the KET-F states.
Right.
The KET-Fi
All right. Good. That's it.
Yeah. Thank you.
Yeah.
Yeah.
Have you thought about making the circuit sparser by making it sparser?
Yeah, so we have thought about that. Yeah, so another thing you can try to do is try to either make a sparse. Oh, sorry, I forgot to say. So the question was, have we tried to make the circuit sparser by making a sparse? Yeah, so we have thought about that. So we're trying to get this down to depth n times log n instead of n squared, so that it's closer to practical implementation. I think like making a sparse doesn't necessarily make the circuit itself sparse, but you can take like some structural properties on A that will ensure that the number of terms that you get for f prime is smaller than like order n cubed. Like maybe it's like order n squared log n or something like this. Of course, then you're making the problem easier by adding more structure. So it's again a question of like, is it still classically hard?
Have you done resource estimates for like specific values of n?
Yeah, I don't know if those are public yet.
Okay.
I think those will be out when we put out the paper, but morally it's exactly what you would expect, right? Like it's like the number of qubits is exactly n, and the number of gates is exactly the number of coefficients of the polynomial. So like, it's slightly less than n cubed, right?
Yeah.
So you can take n to be 200, and like 200 cubed is like the number of gates.
So how does that compare to the estimates for Shor for elliptic curves?
Yeah, I think it's less than like the gate. Well, the qubit count is certainly less,
right?
And I think the gate count is also less. Maybe Greg can correct me if I'm wrong.
But is it sort of dramatically less or just somewhat less?
I mean,
so the gate count would be like around 8 million, like something.
Yeah, the nice thing about qubit 200 is that 200 isn't very big compared to 1,000.
Yes.
So yeah. So that it feels. I mean, that's like roughly, I guess.
Yeah.
X squared mod n gate cost territory, not factoring the Shor's algorithm territory.
Right.
In terms of gate count.
But with far fewer qubits.
Right. Indeed.
Yeah.
I see. Okay. So the advantage over X squared mod n is the qubit count.
That's right.
So this is awesome. I mean, I hope that this stands. One thing that worries, I don't know if you know this, but like 15 years ago, I had a proposal for how to instantiate Simon's algorithm. And the proposal was exactly use low degree polynomials, find the Simon structure using a linear transformation. Right. So it's like F. Oh yeah. So it's like f of ax, right?
Right.
And then what happened was I posted about it on Math Overflow, and it was and there was a classical algorithm to solve it. And the way that the classical algorithm worked was by looking at the discrete derivatives of the polynomials.
Oh, interesting. Interesting.
So then I got scared off from using like low degree polynomials over GF2 to instantiate these things. I never tried it for forrelation.
Right.
No, why not? But yeah, I hope that this stands.
Yeah, me too. That's, yeah. So maybe we should also post it on Math Overflow. I mean, at least like ChatGPT could not. Okay, so let me make some like final closing remarks. So as I said, like we're using these self-dual bend functions for the FIs. So one interesting fact is that increasing the degree of F seems like it should make it easier to invert the affine transformation, because if we go back to this PRG picture here, then like if you had a higher degree polynomial, you're still going from like n squared bits. So like the number of coefficients is still linear and the size of A is still n squared, but now you're mapping to like n to the 4, n to the 5, like the number of coefficients of this like larger degree polynomial. And now you're really demanding much out of this PRG, that it has like very large expansion. So it might be, like easier to distinguish from random in this case and potentially to break it. You can also think of it as like, I have way more equations if the degree is higher, and that should only help me to solve the problem. So it could be that like degree 3 or 4 is like the sweet spot for this sort of thing. Of course, the million-dollar question is like, is the sign of the forrelator actually hard to compute? Classically, the estimates for like the number of gates assumed like all-to-all connectivity, because this polynomial that you're getting after the obfuscation is going to look fairly random. So it's going to involve interactions between like random groups of 3 qubits. This is again like by maybe adding extra structure to A, you can sort of prevent this and make it a bit more local, but then again, you're making the problem a bit easier. So it's a question of, again, like classical hardness. And you can also, kind of as like Scott pointed out with Simon's problem, you can also use this approach in other cases as well. So we didn't think about using it for Simon's problem, but you can also do it for like IQP circuits, or like other families of like problems like this. So this was a question that was also asked, like, is there even a quantum algorithm that can invert this affine transformation? So we don't know. Like quantumly, you can compute the forrelation, but it's not clear that you can actually recover A itself. And I was also wondering, like, are there any benefits to going to like k-fold forrelation, which is like BQP complete? Like, could that give us anything interesting? Which is unclear. And finally, like, are there other obfuscation-like approaches that we could take to try to resolve these challenges? Okay, so that's all I have. So thanks, and I'm happy to take more questions.
So thanks, Andrew, for a great talk. Let's just do very brief questions, maybe, because we had a bunch during the talk. So maybe we can do 1 or 2. Anyone?
Yeah.
So you alluded to how the correlation is BQP complete.
Yeah.
And the proof here is like you sort of instantiate, you pick functions that sort of instantiate your quantum circuit for k-correlation.
Yeah.
I'm wondering, can you frame this, like say 2 correlation problem in terms of a quantum circuit implementing your low degree polynomial, and then you sort of, let's say your function is sort of like a random low degree polynomial, then you sort of have like a particular architecture for a random circuit, right? So like, I guess the question is, can you relate this to random circuits that have a certain structure?
Oh, I see. So basically the question is, can one relate the circuit that we get from this obfuscation approach to some sort of like random quantum circuit? Yeah, it's a good question. So I'm not sure. I mean, in the k-fold correlation case, I guess it would kind of look like a random quantum circuit, right? Because you'd have Hadamard's, then you'd have like a random looking polynomial, then Hadamard's again, and so on and so forth. Yeah, I'm not sure if you could view it, like it does have this kind of structure embedded into it. Like the problem has this structure into it where it's like, you apply a bunch of Hadamard's and then you just do phase gates to implement the terms in the polynomial. Maybe if you do like some clever compilation technique, you could then turn this into like a smaller circuit that is like even more random looking, but I'm not sure. Any other questions?
In your cartoon, I like that Forrelation was literally the dark horse candidate.
Yes. I actually asked it to not make a horse, but like a function that looks like a horse, but it wasn't able to do that.
Okay, maybe we'll take the rest of the questions over the break. And there's also a panel session, a panel discussion this afternoon. So if you want to ask questions of all the speakers, you can save them till then. But let's thank Andrew again and take a break until 11:05 for the next speaker.